introduction.
Good morning, everybody. I am Yonsei Lee from Seoul National University. I'd like to introduce the keynote speaker. Actually, I was a keynote speaker in the last year, so I'm very happy to come back and meet you again. I was, in Korea, there is an institute similar to IEEE. It's called IEIE. And IEIE and IEEE, we have a very good relationship, sponsoring a conference called ICCE Asia, held in East Asia region. So I hope to continue this good relationship between Korean IEIE and IEEE. Okay, so let me introduce Professor Sanghoon Lee from Yonsei University. He received his PhD from the University of Texas at Austin. He worked at Lucent Technology in the United States before he joined the Yonsei University. He served as a general chair of IEEE IB MSP workshop and also served as editors for a number of IEEE journals. For example, he served as associate editor for IEEE transactions on image processing and also IEEE signal processing letters. Later, he has been serving as a senior area editor for the IEEE signal processing letters and also a deputy editor-in-chief for the IEEE transactions on multimedia. So please welcome Professor Lee.
Thank you for a nice introduction of me. My name is Sanghoon Lee. I'm IEEE Fellow for the IEEE Signal Processing Society. And today I would like to talk about leveraging multi-camera systems for Avatar and Vihan. Yeah. And Las Vegas is a very nice place. I have a very good memory to bring my family to enjoy a lot of funny things in Las Vegas. So it is very honor to me to present my talk today. And here is the full 3D sensing technology. One is a passive stereo, where we're using a two camera, right? Between two images captured by two camera, we can estimate the depth. Second one is the active stereo. In the middle of two camera, we put the projector. That projector produce some pattern. So if you take a look at the photo, right, you can see a lot of patterns projected on the object. Based on the pattern, we calculate the depth. So depth is much more accurate, right? And third is the structure, right? So we also project a stripe pattern. Based on the phase information of the pattern, we can calculate the depth information as well. But in order to install the multi-camera system, right, such as stripe pattern overlap, and that makes a lot of interference. So using single structure light camera and single projector, right, it is very nice. However, we have some difficulty to install the multi-camera system. And also, the last one is a time of flight. It is a simple. We just project a wave, IR wave, from one laser source. After measure the turnaround time, right, we can calculate the depth Of course, it would be very difficult to install the multi-camera system using this time-of-flight sensor. So Max Planck Institute installed the active stereo and to measure the depth information. So in the Max Planck Institute, they have a 3D scanner, right? And so here they're using 22 active stereo because as I mentioned before, active stereo is quite robust to measure the depth information. So they measure the static humans, right, using 22 active sensor. And also, they measure the human face. So if you take a photo down here, right, a lot of patterns project on our face, and they measure the human face using the 6 active stereo and 6 RGB camera together. And so here is another example. Not only the static object, but also the moving object, we can measure the depth information. So this is a figure. They shooting the active stereo pattern on the body. Using the pattern, we can capture the human body information, left and right hand side camera, and measure the depth information, right? After this measure, the human body, we can build up the human shape. So this one is the after measure the human body, right? And then they develop human body model, such as it's called the SMPR model. In this model, we use 7,000 vertex to represent human body, right? So actually, this body is a parametric and statistical and linear body model. The Max Planck Institute, they announced this body model is 2015. So how can we implement parametric model? After capture the human body, right, we have a massive 3D scan data. Each person, we use a different vertex when we capture the human body initially. However, according to the body model provided by the Max Planck Institute, we can regularize control the number of vertex into the around the 7,000 vertex, which is called a registration. After register that template into the template body, then we can do some principal component analysis. Actually, this principal component analysis is a Fourier transform. So using the coefficient of each energy, right? Here we have 3 different components. These 3 different components is orthogonal with each other. So just like a Fourier transform, right? We can control the coefficient of each basis, right? So after we calculate the value of a coefficient, right? We can construct the human model for each person. So SMPR model is like a parametric human body model. It's announced in 2015. So not only the human body model, but also human hand model and human face model put together, and which is called the SMPR Express model, which is announced in 2019, right? And to represent more detail, but with human expression more additionally, right? And so they present XMPR X model 2019. So Microsoft also built up camera systems, right? And here I represent the size of camera system is 2.8 meter and 2.5 height, right? And they build up RGB camera and IR camera together. So they build up 53 pieces of camera, and the frame rate is 60. So in the Microsoft, they try to get the mesh information and using the standard, and they just compress the mesh information, and they are ready to transmit this 3D shape into the from the transmitter to the receiver. So they are they want to service 3D this mesh over the networks. So they build a pipeline, and they get this detailed texture information. Actually, it is quite difficult to put this texture information into the 3D objects around 2015. So actually, I think a lot of people get involved in to make this texture information for given the 3D shapes. So nevertheless, they just demonstrate this type of things. And Google, they present their own studio 2019. Actually, the size of this camera system is 4.0 meters. So they build up the dome type camera systems. In here, the RGB camera, each specification is 12 megapixels, and so they put the RGB camera 58, and IR camera also they build on the IR camera is 32s and 16 project as well. So they capture the 4D face and body. Actually, 4.0 meter is a little bit large size. So it is enough to capture the 3D human face as well as 3D human body. One particular thing in the Google system, they put installed the LED, RGB LED module. So around over 300, right? They put the RGB LED module. So this figure, when they just turn on the RGB LED module, they just they can represent arbitrary surrounding information. So they also represent this very natural light controls. So this one is their light control system. Not only the capture the whole turn on the whole LED module, but also they turn on a particular LED module to represent some diverse lighting environment. So this one they call the one light at a time. So they presented this technology, right? And so this is a final result captured by the Google Studio. And actually the engineer, right, and they are work one company, and next year they move to another company. So it is very easy to make a performance comparison. So they announced that their detail is much more advanced compared to the Microsoft. Yeah, so because of their natural RGB LED module, right? So we can put these objects, human object, into the background more naturally. That's the main advantage when we using RGB LED module. So they make a comparison between Microsoft and Google Studio, and we can get much more a little bit advanced high quality compared to the Microsoft. And 2021, Meta, they announced another camera system, and their size is a little bit smaller, and 2.2 meter. compared to the Google system, they using the 4 meter, right? Meta Studio, the size is a little bit smaller, and 2.2 meter. It is quite difficult to capture the whole body. 2.2 meters, it is very specific to capture the human face. And so they installed white LED, not the RGB LED, right? And so, but as you can see here, right, the number of cameras over 140, right? So they install a lot of camera into this small dome system. So this is the one of the example to how they get the human face from their camera, right? And according to the technology produced by the Google, they also installed one light at a time, OLAT camera LED lighting techniques into their studio. Likewise, this is a camera system built in our laboratory, and so also we follow up the Google system. So we installed RGB camera system in our laboratory as well. In our case, a diameter in our laboratory is 3.6 meter, which is a little bit less than the Google, but we would like to capture the human body as well as the human face. We installed RGB LED module and white LED module together, and we build on the RGB camera and monochrome camera together, and then we try to capture the 4D face and body. And so we implement photometric stereo, right, using changing the camera pattern, LED pattern likewise. And so when we control this pattern, we can get a normal vector of the human body. So this one is after changing the LED pattern, right? We can get more high quality normal vector out of this human body. So if you take a look at this image, right? And this is a normal vector image. And if you take a look at this image, you can see a very detailed wrinkle information of the human body. As well as if you take a look at the face, right, you can recognize who is this guy. Actually, this is my student, but we can identify his face very accurately. And not only the white LED module, we installed the RGB LED module, just like Google system. So for given the photo, actually, this photo, you can get this type of photo from using your camera. So actually, if we provide this photo, we can measure, we can estimate the lighting system out of this photo, and using that light information, we can control the light in our camera system. So we synchronized our camera LED information as just like the camera RGB camera, right? You provide from the user, and using the camera. Using the light control, right, we can project the light to the arbitrary object. After get that light object, we put that object into the image. Then you can see the object looks like stay inside of the image because we just control and synchronize the lighting system provided by the camera. right? So this is one of the example I would like to share with you. And user provide a two input image pair. So user capture one image in the front, and then capture another image from the backside, right, using the camera. And if they provide these two images, we generate a light environment for the user, right? And then recently, AI technology has been developed, and so providing two images, we can also generate HDR image. So for a given HDR image, we put arbitrary object inside of this image. So we can synthesize any type of combination between the 3D object into the 2D image. So this is the first performance. We got the first generation camera system. As you can see here, when we get the 3D meshes in the middle photo, we got a lot of blur, effect. After refinement, we can get a more detailed human face in the first generation camera system. Nowadays, we don't do such a refinement. If we're using the camera system, we can get rid of all the noise. And so this is the final result we got recently. So actually, we get a lot of detailed face information out of the camera systems. Okay, so I would like to discuss about the 3D Gaussian splatting, which is the most hottest topics nowadays. Every company just, concentrate, invest a lot of money to implement this 3D Gaussian splatting. So in our field, this one is the most hottest one. And so what is the Gaussian? Gaussian is just like 3D small Gaussian sparkles, right? We put this 3D Gaussian sparkle in the 3D space. So this Gaussian parameter consists of position information. Position information is the location information in the center information, right? And covariance, of course. Actually, we control the Gaussian shape using the variance information. So we can control the scale and also rotate, because we put this Gaussian split information into the 3D domain. And also there is a parameter opacity. If opacity turn on to equal to 1, then it's a perfect opacity. So nothing can be seen behind of these Gaussian sparkles. However, if we turn on the opacity is 0, then this Gaussian spread is a perfect transmit. We can see any Gaussian sparkles behind of this sprite. And also, it is quite important to implement color information. So using the spherical harmonics coefficient, we can control the color. So using this technology, we can represent 3D space color information of these small sparkles. So why it is so fast? Compared to the previous volume rendering, such as NURF, the Gaussian splat just splat. So if you take a look at the right-hand side image, right, we have a Gaussian sparkles on the 3D space. This sparkles is splat into the image space. And using the ground truth image of image space, we can control the location and opacity and also the color of each Gaussian splat. So that's the reason. That's the reason why. How can we using this splat information to render the image space? actually the ground truth image is 2D dimension, right? After splitting the 3D Gaussian split into the 2D image, we compare to the 2D ground truth image. That's the reason that's reduce the number of information to calculate in the GPU. So it is quite so fast, and then it is quite, reasonable, very nice quality of the image, rendered image quality. We can obtain the very nice rendered image. In order to represent 3D color, right, in the 3D space, this is a type of technology. How can we implement color information for each Gaussian sparkles? So actually, this is a round trip color information are orthogonal with each other, just like a Fourier transform basis, right? Each one is become a basis. We control the coefficient of each basis and then implement 3D domain color information. So here we have 9 coefficient we need to each color. We have RGB color, right? Each of them have 9 coefficient, right? So 9 by 3 is 23. So 23 coefficient we need to represent the color of each Gaussian particle. So this is a rendered view, right? This one, the number of Gaussian particles is 3 million. So using the 3 million Gaussian particles, right, we can get the rendered view of the 3Ds. And also, we represent the dynamic human motions. So each particle follow up the 3D object to control the moving object as well. So for the Gaussian splitting has been also deeply studied in our field. So I would like to mention about the Gaussian avatar. For a given the 3D mesh, right? We initialize the location of the 3D Gaussian sparkles. So this is one of the examples to locate each Gaussian sparkles in the 3D space. So here we have a small Gaussians. And also, in order to represent a 3D object, we have a vertex as well as we have a face. So for a given the face in a polygon, right? Inside of 4 polygon, we put the Gaussian split inside of 4 polygon initially. After put the Gaussian sparkle, right? We optimized location and then variance and color information using the 2D images. As we optimize, we do some density control. So each phase we have one Gaussian sparkle, but in order to represent the detail, right? The Gaussian sparkles split into the several small sparkles as well. So in this figure, you can see one sparkle is spread into the 3 different sparkles to represent very detailed texture information of the humans. So Google Meta announced some their own Gaussian avatar, CVPR last year, 2024. As I mentioned before, right, they control the lighting system, and also they have their own human body model, and they have all technology inside of their company. So using their 3D space, right? This is actually animate avatar, and they control the normal vector, and they control the light, they control the emotion of a face and something like that. This one is they control the spectral lighting as well. It's much more realistic, and also they put their human into the background more naturally. And so it is quite difficult to represent human eye and hair and then mouth and then tongue and something like that. And so they present very perfect they present very perfect human avatars. And also they trying to the real-time relighting and also a lot of things. So this is a mechanism. Here is the like a decoder, and we have inside in the input parameter is just a parameter to express the expression and also camera pose. And so we control the camera pose and expression. That parameter plug in the decoder. After decoding, we got the 3D meshes. So for given these 3D meshes, we initialize the Gaussian splat parameter for given the static mesh. Now on top of the static mesh, so we learn about the dynamic Gaussian's parameter as well. So this is an example how they work. For given the static mesh information, on top of the static mesh information, we also adding additional Gaussian parameter to represent 3D motions as well. So this is some examples. So and also this guy is put out the tongue out of his mouth. So it is quite difficult to follow up such a technology. So in our laboratory, we don't try the tongue out of the mouth yet, but the rest of them we just measure the performance and then try to make a comparison. And also they Meta announced 2024 about the relightable system. So here, since they have a internal camera system, right, and they build up their own data set, and so they based on their data set, they implement a baseline to represent identity and expression as well. And then they implement this baseline. And this is what their application. So we can take a photo, right, from the phone. And so we just capture the moving sequence, right? And then apply this image into the AI algorithm. We can do some fine tuning. So using this fine tuning, right, we can we can do some realize this express 3D human animation, right, for given the input video sequence. And so this is one of the example. How can we extend their application? So the first one is just the input image, but the rest of them are animate and also identity transfer from one people to the another peoples. So they, in this case, you can see they control the light as well and expression and all the things. Okay, so in our laboratory, and we are trying to do such things. Actually, you know, this area is the industry put a lot of investment, and so their technology is so fast. Actually, when 1 year ago, I think it is quite reasonable time to follow up the technology. But nowadays, we are trying to, analyze what type of problems when we implement 4D avatar using the 3D Gaussian splatting. So in our laboratory, we also using the RGB camera system, we can get the SMPR model like this way. And so this one is the input camera image, right? Using the single camera, we capture the 3D objects, right? And then using this single camera information, we extend this single camera information to the different point of view you are using the data set. So this one is that Gaussian splatting result. Using, even though we got the single camera capture the image sequence, we extend, we view different point of view and different angle for these humans. And this one is normal vector as well. We got the normal vector using the 360 degree, right? Yeah. And actually, it is quite difficult to represent wrinkle information. Here, in our laboratory, right, we using the database, so we represent more detailed wrinkle information of this human body. So we also control the light as well. In our laboratory, we also control the RGB light system. So we produce a render image with a different light system, right? And here is the overall mechanism. So out of input video sequence, we got the material information of these objects. So roughness and normal vector out of this input video. That's the first step. And second one is the natural color information, which is called albedo. We take out the albedo information as well, and we also control the visibility. It's the visibility related with occlusion. So, and then we set up the light control environment. So we got overall video. So here you can see a lot of detailed texture information we got out of the camera system. Since we got actually build up the database, it is a high advantage to get the detailed texture information, to get the detailed wrinkle information as well. So here you can see the wrinkle information of the cloth is very important and very difficult technology. And so, but compared to the current state-of-the-art information, we can get more advanced this information. So we make some ovulation study as well as we make performance comparison with state-of-the-art technology. And so this is rewritable Gaussian human avatar, not only texture information, but also normal vector we obtain. And also we control the light as well. So this is we got, right? And also, as I mentioned before, in the Meta system, right, they have a static color and static opacity. On top of static information, they put the dynamic color and dynamic opacity information. They using the this controlled Gaussian parameters to render this image. And so here is the example. So we also follow up and also develop our own technology to represent 3D human images. And this is my student, and we are capture my student information into the Obama, right? And so, and using the initial Obama's information, right? We just transfer expression of my student to the Obama 3D Gaussian splat. So we just pass the expression information into the Gaussian splat to the Obama. But there are some limitations I would like to share with you. Actually, when we train, right, we don't usually open the mouse. However, if we open the mouse, new type of object comes out. In such case, Gaussian splat doesn't work quite well. So this is how much blur we obtain when this guy is, my student is open the mouse, right? Inside the mouse, there is a teeth. Teeth is, new ones, right? And so the object is comes out. So in this case, it's unseen teeth in terms of the Gaussian running. So we got a lot of blur in the teeth. And also, sometimes if you provide some bad light condition as a ground truth, right, we got some bad result. So this photo, right, right-hand side, we got a lot of highlight. The light is so strong, so it's quite light is unbalanced. So in such a case, the performance is not quite good. So this is the splat image. Then you can see a lot of blur and a lot of color distortion we can observe from this event, right? So if we reanimate these things and the input information is not quite correct, right? Also, we have a lot of difficulty to implement Gaussian splat. So this is a type of limitation I would like to share with you. And also, in order to overcome such a limitation, so nowadays a lot of technology has been presented. And so for a given single image, right, for a single face, this is a one face. And using the one single image, we try to construct a 3D human shape. Using the AI technology, and we synthesize different view of the human face, and then get rid of some bad things, and we only select very solid 3D human face, right? And then improve the image quality from the image processing technology. And then not only the front view, but also backside. You can see the backside, we also emulate. And then we generate the 3D human shape from the single to the full 3D. Right? Using that generated information, we implement Gaussian splat. So this is some of the examples for a given the single image, right? We generate the backside of the hair, right? And then after get all the information from the AI technology, right? We can also animate this one. So this one is also example for a given the single photo, or we also implement 4D. We can implement 4D. I mean, but here is the demonstration is how to we get the 360 degree the human shapes, right? So that is our current status of the technology in Gaussian splat. This is the end of my talk. Thank you for your attention. Okay.
So because of limited time, we will take just one questions. Anybody has any questions?
Raise your hand. Raise your hand. Time for a couple questions. Comments? I'm never going to watch television or the movies again and assume that what I'm seeing is real.
Actually, I have one question.
Okay.
So actually, I think your avatar is very, very, very impressive. I'm wondering the complexity of your computation.
Yeah.
So like how much computing power is necessary to process in real time?
Thank you for your nice talk, nice questions. Actually, let's see. I would like to briefly share with you how much difficulty I have to get this one. So actually, this is the computation times to get the 3D shapes. Actually, when I start the beginning, right, it takes maybe 1 or 2 days to get one 3D shape. So it's maybe 4 years ago. Nobody want to set up the camera system because in order to get the 3D shape, right, it takes 1 or 2 days. It's impossible. But nowadays we are trying to optimize this to obtain this system. So we reduce down to the 40 seconds to get one single, object is static shape. So in order to get this static shape, we down to the 40 seconds. Even if Meta and even if Google, we have some bottleneck to get the 3D shape in terms of GPU power and then computation cost. So I think the major company, they cannot reduce the time right, to get the 3D shape less than 20 seconds. That is a current status. So it is quite difficult to get this one 3D shape. It's impossible to real time, even if the Google.
Okay. Yeah. Thank you very much. So our general chair, Professor Todd, will present a certificate of appreciation. Yeah.
Thank you very much.